we're recording. And we can start with some homeworks if y'all want. But if not, that's fine. We can move on.
I currently have no questions.
No questions.
Well, I'm proud to say I did
Okay, good.
I did have one question. I was able to figure it out, but the way they worded it, I was just so confused. Like, there's just so much math rhetoric in there. So
Let's do it.
I think it's towards the bottom.
We can
It
work.
might be 13.
13? This one? All right, cool. Let's talk about it. Tangent line to a smooth curve, this. Is the line that passes through. Parallel to that. Yes, yes, yes. So use your original and your velocity to find parametric. Oh, easy. Okay. You're right that it has a lot of blah, blah. But because I've been used to listening to their blah, blah, yeah, I know. You get used to it eventually. Let's do this thing. Yeah, this is fine. First off, let's zoom out and talk concept, right? So we got a curve, and we have a point, and there's this velocity vector at that moment, but there's also the position where it currently is located. Well, we call this R, and we call this R prime. And that's why they're talking right here, use R and R prime to figure out what's going on. So far, so good? Okay. They're kind of like saying point slope in a way. Point and slope. R prime, P for point, V for velocity. So yeah, that's what they're blah blahing about. So what we want though is to do this R, and we're going to find the derivative. Then we have both of the things we need, right? All of our like pieces. And they said not T, but T naught. So just like basically plug in 6. So we're going to have R and R prime, plug in 6, and then we're going to mush them together into a single like formula. Sounds good? Let's do it. So I'm going to write both R and R prime up here because I'm going to plug it in, and I want to make sure that I plug it in correctly. So give me a second to just basically copy it down. And then we're going to do some derivative action. But yeah, this is a good question for sure. I mean, they're all good questions, but because it's so blah blah, you know, it kind of sometimes wants to throw us off, you know. I'm just going to put this T naught as 6 on the side so that I can start doing derivatives and stuff, like full screen. So we have our R, and I'm going to have my R prime. What's my derivative? What's derivative of ln?
So that would be 1 over inside and then
Yep.
derivative of inside.
Yes. Yes, exactly. 1 over stuff, derivative of that stuff. And the derivative of that stuff would be
That would be 6 over t.
Or 1 over 6. Am I right? Should just be, what's the derivative? See, this, it's almost deceiving, right? But what's really going on is this. And I'm saying, what's the derivative, right? We're going to get to that. I'm not done. You're right. So that was the derivative from the outside. But then I have 1 over my stuff, which is that 1 over t business you keep telling me about. Come on, Chad. It's this guy. I know. And so I did it. Okay, fine. Because we were talking about the derivative of the inside. Fine. I know I mess up a lot. Okay. Yeah, I know, right? So that's my derivative. 1 over stuff. Derivative of that would be the 1/6, correct? But now, like you were saying, though, it technically flips, and the 6's should cancel, right? So let me go ahead and just start doing that. You said it's 1 over t eventually. Is that right?
Yeah, because that's 6 under.
Okay.
Flip up to the top.
Have you done this problem already?
Oh yeah, I already.
Oh, okay. Give me a chance. Give me a chance to do it. So, how would I get a derivative of that fraction? Put it on the top. I like that. And then do the product rule thing. Yeah, definitely. We could also do quotient rule. If you want to do that. Mason, did you do this one? What did you do? Yeah. You did quotient rule? Okay, I'll do quotient rule. Let me remind myself. Low d high minus high d low divided by the square of what's below. I almost always have to sing it out, for me to remind myself. So then the derivative of the bottom is, the top derivative of the top is 1, right? High derivative of bottom is 1 again. Then we got this square thing. I kind of ran out of paper. Wish I can copy and paste that over there. Is there a way to make this easier looking? Surely. What happens? Very good. Yeah, those t's are going to cancel. And that would be a positive 6 plus a positive 8 makes a 14. So 14 over that blah. We're going to be plugging in a number here in just a minute. So, blah or not blah, it's going to be fine. And then derivative of this thing, that's definitely product rule. I'm gonna actually just have to do it on the side here. Ugh, I hate having to do that. But we got f and g, and so then we're doing f prime g plus f g prime. So 1 times the ln. And then I leave the t alone. And then we already found the derivative of this guy, right? So what does that end up looking like? 1 over t, and they cancel, yes. So we get our original plus 1, essentially. Okay, awesome. Sorry for all that side business there. Okay, so we have my point, and I have my slope, essentially. Now I just need to plug them in. So if I plug in my 6, then I get ln of 1 is a good. When I put a 6 up there, sweet. And if I put a 6 and then well, it's already a 0. That's nice. That's actually really cool. Our prime of 6, when I plug in a 6, 1, 6, very good. When I plug in a 6 here, that gets a 14, doesn't it? But then it cancels a little bit. 1 over 14, because the 14 in the top will cancel with one of them in the bottom, but leave one behind. And then right here, we already know this one. That's going to be a 0, but 0 plus 1 is 1. So those are my slopes. And now I just need to mush them together. And just what we're doing is the mx plus b every time. I mean, that's really what's going on. But we can't use y and x because we're doing those for other variables, right? And so it's kind of like x is equal to x naught plus at. And I know I flipped them and I had to use a different letter, but it's ultimately the same stuff. And we put a t with that guy, and then we're done. Okay, so then my, I guess, what would I call this? What would I call what I'm doing? Velocity vector? What do they call it? Did they have a name for this thing? Oh. Okay, so they just call it x. All right. So there's your formula, I guess. Yay. So yeah, we got 0 plus 1/6t, 0 plus 1/14th t, 0 plus 1t. So there's my answer. Let's check to see if that's a thing. I'm going to minus this. Nope. Wanted to pull it back up. There we go. So we had 1/6, 1/14th, and then just 1. Which one? Yeah, you see how they got those T's in the bottom there? That's no good, right? Trying to slide them in there. Very good. Is that it? All right, cool. Good. It's a good question. Other questions? Correct. You would have a number there. Very good. That's right. And it could be in the back or leading. Normally, algebra, we put it in the back, but I've seen a lot of times in the front. So, up to you. Cool. Got another one for me? That was it? Okay. If you got something, tell me. And if not, that's okay, because the new stuff is very easy. And we like easy. Good for now? We can always do some more. Like, again, if you have questions, I'd always rather do questions than lecture, even if it's outside of these typical days. You know what I mean? It's like even next week or whenever, tomorrow, any day. Let's start on this next stuff, and you're going to be amazed at really this is very simple stuff. Okay, so it says several variables. What we're used to seeing here, what we're used to seeing here is f of x, and that was really good. That worked for how long? A long time. And now we have f of x comma y, and eventually f of x comma y comma z, and that's it. That's what we're doing. Is just we're adding another variable in there. Okay. What this is here is a two-dimensional. Now we have a three-dimensional, right? What would this then be? It would. It would be a fourth dimensional. It would. The problem is we can't really graphically represent that very well. It will come up though, so just be prepared for it. What we use is this thing. We call it maybe like a heat map almost, where you change its color over time. Okay, so you would have like some three-dimensional shape, and I'm just going to make like a little paraboloid, but then we would like transition color from like a little bit, and then it's like, and then that shows like a change in value. Okay, not right now, not right now, but like eventually when we get more complicated, we'll see that kind of stuff. Now I think that this is a lot of blah 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 going on, but we have seen this stuff before. Boundary points, closed, open. It's fine. I don't think we need to focus too much on that. Okay, when it comes up, we could talk about it. Otherwise, let's keep moving. But there are whole classes devoted to bounded. I don't think we need it right now. And so there's a cool little shape here. These guys in the bottom are the level curves. The level curves. That's their like name. It's just kind of like for a map. Y'all know maps. Here, I'm going to make a map right quick, okay? Like a 2D map. So if I had something that did something kind of like this here, yeah, and then like over here, yeah, I'm just making a map for you guys. Have y'all ever read maps before? Yeah. Yeah. That's a good one. That's good enough. Let's talk about the map and how we can read it. Okay. These are contour lines, right? What this is indicating is either a mountain or a hole, right? Because it's just kind of like circles, and they're all kind of close together. So you can either fall in or you can have to climb it. And we can't tell from just looking at it. We just know that that's what's going on. And then we have this cliff here. There's like all this flat plain here, and then we got a cliff, and it goes up really steeply, and then it kind of just levels off over time. And so if you were to look on it like as a 2D level, right, this point, it would kind of like look like this, and then it would kind of start to level off. That's why it's really close together for a little bit, like lots of lines, and then it kind of just, bigger distances. Says there's not a lot of change. And then this guy, he would just be like a hill right here. So. Cool? No? Has it been a while since we took map making class? So the idea though is that each contour line represents height, and so when I have a map and I have this line on one end or another, they have like a 100, and then they'll have like a 200, and then they'll have a 300, and then like way over here is now a 400 or something. It tells you how high it is, basically. Okay. Again, this is all very overly complicated, but the idea is that these little lines make pictures. If you have a circle, it makes circular concepts. Okay, first question. What do we do with 0, 0, 0? What do we do with this? Plug it in. Oh my gosh. This is your homework. Don't tell Cal 2 people. Don't tell them, okay? That it's like this way. Make it sound really hard, you know. Oh man, it's just so tough, especially the brand new chapter we started. Right? I almost don't even want to do the others, but I feel an obligation as a math teacher. So, yeah. Are there any questions about, I don't know, just any general questions? We could talk about maps while I do this. I'm sure I can multitask. Oh. Oh. That's a good idea. Because a map itself won't tell you if it's going down or going up, right? It just says there's a change. So having those little indicators is very important. I like that. Oh, for reals?
Yeah.
Oh, awesome. That really helps. Thank you. Um, yeah. And then like I don't want to do these just because they're silly, although I know it's not hard, and like I'm just trying to avoid it. $27. Is it 16? No.
I always want to say it's 22.
Desmos. I mean, why am I? Yeah, why am I even wondering? You know what I mean? Why do I even wonder? You're saying it's 22?
I'm pretty sure it is, but I'd rather double check.
Oh, me too. Oh yeah, good, good. And we're good with that. No need to keep going. Last one, just so that I can say that I did it. Whenever I square these, though, it is going to be a lot easier. And so the we got 144, of course, in the top, but the square root and the square they cancel and just leave the plane 3. Same with this guy, and same with this guy. Notice common denominator, blah 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 blah, Desmos. It should have been a 3. There we go. And we leave it like that. Let me flash the answers right quick. Yay, they did work. Whatever. Good with plug it in? Yeah. Figure so. I'm happy with plug it in. Moving on. It says sketch and find a domain. So we have an ln. Now I want to just break this back down into something that's more manageable for us. What if instead of all this, what if I did this instead? Okay. I'm not saying that this y is this y. No. I'm saying that this is a 3D, this is a 2D. What would it look like in 2D? It might help me in the 3D. Yeah, that's kind of what I'm going with. Well, again, let's just assume that I don't have Desmos graphing. and I want to graph it. How would I find the domain? How would I know where I have a graph? Set the inside equal to 0. Yeah, exactly right. And then we can see where those asymptotes would be, or at least the start for where we want to go. Move it over, square root, right? So in a way here, like it's just a rough graph, it would be at 7 and -7, and then I think it's either in the middle or it's on the sides. Now, what if I plugged in a really big number here? Would it work? Like if I plugged in 100, a million, would I get ln of a million? That's okay? Yeah, that's fine. What if I plugged a small number in, like 0? Would 0 be okay there? Because I would end up with a negative in the end, right? So like basically this is no good. It's something like this. So that's the 2D version, is like it's coming out from -7 and 7, okay? So I want to keep that in mind when I go to these options down here. Now I know there's a lot of words. I would ignore that for a minute and let's just kind of look at this stuff here. Where do you think that this is touching? What's that number there? 7. Because it's all it is here. We're going from a 2D to a 3D. Okay, that's all I'm doing here. And you can note how I did that. So for sure, it's like a 7 thing. A, B, C, or D out of these options, which one do you think would best match up to 3D version? It would be A. Because again, my 2D version said we start at 7 and -7, and we go out from there, right? Basically, like all of this stuff is what I want, is the outside stuff. So that's what I'm looking for here. I want the outside stuff. Mhm.
That's also led to the word equal that to 0 as well. So I was curious on if that's another way we can identify.
Oh yeah, yeah. I'm just going the 2D route. We're gonna do that. I will do that. Cool. Good idea. Good idea. In a way, I'm trying to say, we can do this by just kind of looking at it in a 2D way, very similar to what we've already done in the past. But you're right, James. I mean, really, what we need here is to do it properly. You don't come to me for proper. But yes, we have ln of stuff, and what do we do to find the domain? We do the inside equals 0, right? And so then we set this equal to 0. And it's not like we're solving for a single number anymore. That's the thing. We can't just say, I want to solve for a number. And so the best idea is to get it to something we recognize. That's a circle, right? That's a circle, and you can say that my radius is equal to 7, which we kind of proved last time in a way, right? So we got a radius of circle 7. Wait. We have a circle with a radius 7. So this one clearly doesn't work. This one clearly doesn't work. It's going to be one of these two guys, right? And now I need to know, do I want inside the circle or outside the circle? And that's when I start plugging in some numbers. What would be an easy number that's inside of the circle? 0, 0. Exactly right. Yeah, you guys got it. 0, 0. So let's try that. What happens if I put a 0, 0 in to the original? ln of a negative. I mean, that's like not even imaginary, man. That's like no good. So, yeah. So this is no good. That doesn't work. It would have to be something on the outside. Cool? Okay, awesome. But what about these words up here, right? Choose the correct description. And again, we're doing like the best description possible. So x squared is less than or equal to. I think we need to be like greater than or equal to. And also notice that when they have them separated like this, when they're separate, that's actually not a circle. If you separate them like this, what is the shape going to look like? Maybe. I don't know, actually. I'm guessing here that it's like a square, a rectangle, because you're independently working each variable. So like the x's are working on their own, the y's are working on their own. So I'm thinking that would be a square. Even then, though, none of that really makes sense because that's not what's on the inside. We're saying inside equals 0. So look for the inside and set it equal to 0, right? So like this guy's really good. This guy's really good. This one's good. This one's good. So already we got a 50-50 shot now, right? But we were looking for whenever it's greater than 0 specifically. Notice that ln of 0, is that a good thing here? Can you do ln 0? Not here. We can do square root of 0. That's cool. But ln of 0 does not work. And therefore, I'm looking strictly right here at this guy, greater than 0. So it's kind of like they did the step that we did to get there. Like, find a domain. What do? You set the inside equal to 0. That's what they were doing here. Is that okay? The problem that I have is that MyMathLab holds us back a little bit. It doesn't really want to give the full concept every time. It just shows a part, a piece. We move on, and that's okay. I mean, we can't do otherwise. Yeah, please.
So if the inside wasn't hollow, but it was solid, would that switch how it be where we want to have it say that it's less than 0?
Yes.
Okay.
Yes. Quick example. Let's say that instead I had 49 minus x squared minus y squared. I could tell you all day long that's going to be inside. It would look like that.
Okay.
Again, we set it equal to 0, right? But would 0, 0 be an acceptable point at this point? Yes. What if I plugged in like 100, though? No good. Cool?
Yes, sir.
Yep, exactly. So more level curves. See that level curve thing here. You can see that it says f of xy is equal to c. Well, this is a z value is equal to c. So like they're all the same. Z, c, blah, blah, blah. They're just taking what we have and we're setting it equal to each of these numbers 1 by 1 by 1 all the way down. We're just setting all these different numbers to it and solving. Surely that we can find a pattern though, right? That I don't have to do that manually. That would take so long. So let's do one of them and see if I can recognize a pattern maybe. Make sense? So then 2x minus 2y is equal to -2. I want to get it to something that I recognize, right? And something easy is y equals blah, blah, blah. That's kind of like my goal. So can I get y by itself? What do I do? Oh, you like moving the y? Okay. Advanced techniques. Yeah, I like that. Perfect. Perfect. Very good. Give me a name for what you see here. What kind of graph is that? Linear line. Yes. Exactly. A, B, C, or D, we got A or B now. These guys are no good. We need lines. Positive slope. Positive slope means it's going up over time. Bam. There it is. You got it. I love that. Good analysis. Positive slope. I like that. And there you go. Did you actually have to do it for each one? No. But if I could, if I needed to, I could say that this number right here would change. And so then I can make that into a 1, a 0, a negative, a positive, whatever I need. Yes? Cool. Now here comes the bigger leap. This is the leap here. We're going to take our 2D and go to 3D. Okay? What you see there, do they have the pictures? See, this is where MyMathLab's holding me back. Is this a separate like function? Is this like a new question right here? And I just like mushed it wrong or something? Oh, that's so annoying. Okay, yeah, I think that's a brand new question. Okay, well, we're going to do our own picture, okay? And then I'm going to warn you, it's not perfect, but we can figure something out here, right? Notice that we have these contour lines are straight lines like that. And so that's my map. So then in 3D, would I expect to have parabola? Would a paraboloid make sense with something like this? I mean, wouldn't it be more like this guy, right? That's more parabola looking, right? So I would say no. It's definitely not that. Here's another idea. What about like a sphere, big ball? Would straight lines indicate like a ball? Not really. No. What do straight lines indicate? Like if I went to the next dimension, think about it like this for a second. I got a line and I want to make it into 3D. What would that look like? A plane. It's a plane. And so what's going on is that this is a plane of some kind. And again, not perfect drawing, not perfect, but it would be some kind of a flat sheet, like a plane of some kind. Specifically because they're all equal distant to each other. If there were some that were really close and they got closer and closer and closer together, and then they started like going further and further away, then what's happening here, because they're like really close for a little bit and then they get far away, this is like it's like a parabola, I guess you can say, but it's more like a tunnel. It's more like a tunnel. And so they're really, really close in some places and far away in others. Actually, I think that's inverted, but whatever. Planes or tunnels. Moving on. They didn't ask for that. I don't need to do it. But I just wanted to show, okay? Cool concepts. Okay, here we go. Given this function here, answer blah, blah, blah. So let's rewrite it. And it says find the domain. And that means what possible x values do you have, right? But here in this class, not just x, but also y, because we're using both of those. What possible numbers can I plug in for x and y? 0, 1. You're also writing them down. 0, 1. That was good. I agree with those. What else? What about 2? Is 2 okay? Can I put a 2 in right there?
You can just keep going until the point of where it doesn't work anymore, which in this case I don't think would have that.
Negative infinity to positive infinity. Yeah. You can put a negative in there as well, right? This is whatever. Remember the domain rules? I know this is, I teach college algebra, so I have an advantage over you. Because I could say, oh, don't you remember chapter 2, section 3, question 5? And you're like, no. Do you remember domain rules? I'm looking for 2 specific things. Division by 0. We don't like that. And then square root of negative numbers. We don't like that. Do I have division? Do I have square roots? Here, there's another one. Do we have LNs? Do we have an LN anywhere? So, I mean, we're good, we're good, we're good. Everything's good. Negative infinity to positive infinity. So how would I put that here? It would be A, all points on the XY plane. Now, how would you express that is not negative infinity and positive infinity, right? Actually, I don't know how they would do it. Curly comma? There you go. Yay. I don't know. Don't listen to me, but the idea is all points work. Very good. What about the range then? Again, don't overthink this. The range is going to be a single value, and it's the y value. Well, okay, the z values. Zero, yeah.
Yeah, I'm trying to think back to my college algebra days.
Zero. Well, it's the possible answers. Let's just say it's possible answers. So you say 0. 0 works. I agree. There it is again. Exactly. Negative infinity, positive infinity. If you put in right here 1 million, then you'll get 9 million, right? You put in a negative 50. You put in, you get that. You get any number you put in, you get out. It's whatever. This one is a legitimate one. It says interval notation. You do actually need to put that. And let's verify. I'm going to flash the answers. Yep, see. Flash the answers. Negative infinity, positive infinity. So that's a legitimate one. And again, we can say that for sure because it's a single variable, and that's it. It says, what does this look like? Of course, we can use Desmos graphing, but this is where we need to start learning about all this fun stuff, right? How can I translate that into a three-dimensional graph on my own? What would you do? Give me some ideas.
First by making a table and see how much it expands by.
Have you ever seen a 3D table?
No.
Then let's do one. So yeah, you might not want to write this down.
Okay.
Yeah, because this is more of a show and tell of what not to do. I mean, it's good. It's legit. It was a very excellent idea. Okay, and I'm not saying it's wrong. I'm just saying that you're going to get really sad. Okay, so notice that way I have to put in two numbers at once in order to get a single answer, right? So let's start with something easy, 0, 0. And then I get a 0, right? Because 0 times 0 is 0. Let's start with 1. Okay, so if I put a 1, but there's a 0 there. 0. And then I'm going to do 0, 1, and it's still going to be 0. And then I put a 1, 1 in. If I do 1 times 9, I get a 9. That was just 0 to 1. Okay, and I didn't even hit up any decimals, okay? Let's do 0 and 2. 0. Let's do 1 and 2. So 1 times 2 times 9, 18. And then I got 2 times 2. So 2 times 2 times 9. Yeah, 36. Very good. And then I have to start over. So 2 times 0 is 0, because anything is 0 is 0. 2 times 1 times 9 is 18 again, and we already have the 2 times 2. I haven't even done negatives yet. You want to keep going? This is a legitimate thing, and I will have to break it down like this sometimes. I will have to, but not right now, hopefully. But it is a good starting place, actually. What are we seeing here is that at 0, we have 0, 0. Okay, so I can at least tell you we got that. So that's actually pretty cool. As we progress in octant 1, we get bigger, right? If I keep going this way, 45 degrees out where both of them are getting bigger, then it's going to get bigger. And it's going to get a lot bigger. It went from 9 to 36. The next one here, 3, 3. 3 times 3 times 9 is 81. I mean, you can see how much it's growing, right? It's getting fast. So it's not linear. It's actually growing, not exponentially, but it's growing. And what's interesting about this in particular, maybe I'm doing too much concept. I'm sorry. I'm going to have to do concept. I love concept. It works out great. What if I always have the same numbers every single time? What if I'm saying that x is equal to y when I'm doing all these numbers, right? Well, then instead of saying 9xy, I can say 9x squared. And you know that shape. See? See how I'm creating it? And look right here. There's the other half of it. Along this y equals x line, we have a parabola. Cool, huh? But that's not the entirety of this. Because what if I have, brand new color to kind of throw you off here, what if I had negative? And I'm not just saying any negative, I'm saying that they're negative of each other. So what if I had, I'm going to scroll here a little bit, not 1, 1, but negative 1, 1, right? So 1 times 1 times 9 is a negative 9 this time. Negative 2, comma 2, negative 36, right? Or if I did this way, same thing, negative 36. As long as they're opposite signs of one another, you're going to get a negative. But if they're the same sign, both positive or both negative, then you're okay. So here we go. It's another parabola, by the way. but this time you can see it's the same kind of shape, same kind of numbers, but now it's going to down. So this guy, forgive me for not being perfect here, I'm going to try. This is my y equals negative x line, and now it's going to go down. It's going to go down. So that's a parabola going down. So I have a parabola going up and a parabola going down, and I know we've seen this before. There's a shape. It has a name. What is it? Yes, hyperbolic, blah, blah. I don't know. What's the real name? Right. Hyperbolic paraboloid. That's exactly what it is. What's the real name? Okay. What's the Chad name? Saddle. It's a saddle. But you're right. A hyperbolic paraboloid. My gosh. You're engineering? Just playing with you. Right. Hyperbolic paraboloid, that's exactly the right answer, okay? But in Chad's names, it's saddle. Thank you, Lee. It's a saddle. We got one going up, one going down. You sit yourself down there and you put your legs through it. So there you go, saddle. Do we have saddle here? It says choose the correct description. It's not straight lines, not circles. That looks pretty close. Right? That looks pretty close. And then we got these guys. I don't even know what that is. I'm confused. So let's flash the answer and see what they got. Oh, it's what it's not. And I can definitely describe it. Notice these axes. That's what they're talking about right here. These guys. Yeah. So straight lines, and then the hyperbolas are everywhere else. I want to show you more, but man, only so much time on this silly little question where you just multiple choice it. If you were to draw it from a top view, a saddle from a top view, it would look more like this, little parabolas, but also like this, little parabolas. These here are going up, these here are going down, and there you go. That's practically what's going on, okay? I think I still messed it up, but I mean, the idea is it's something like that. So do you have axes? Yeah, you have these guys. Do you have hyperbolas? I guess so. Whatever. And you can always make a table. So select the correct choice. The boundary. Is there any boundaries? Look, the saddle. Does it have any like holes? Any division? Any square roots? No. No boundary points. That's my answer for that. Is that what they had? Okay, good. We're on the right place. Open, closed. This is basically again saying, do we have negative infinity, positive infinity, or do we have something that's like a set of numbers that we have to use? But we already concluded that we get this guy, right? All numbers work. So I would just say open, because that's what these guys are. Y'all remember the names for parentheses that are open, right? What would closed look like in interval notation? Brackets. Yeah. Exactly. That's closed. So if you had this as your answer, you would say closed. Bounded or unbounded? What do you think? Bounded or unbounded? Unbounded. Yay. I know. There's a lot of parts to it, and some of them are like, what are you asking for? Yeah. It did say that? No. I'm going to be upset. Okay, how's that? Both open and closed. Let's go back and look at definitions, okay? They might be wrong. Thank you for pointing that out. Okay. So open means every point that we have. Closed contains all the boundary points. And the boundary is literally just the boundary. Closed contains all boundary points. Here's some more. Open, if it consists entirely of interior points closed if it contains all of its boundary points. But those are still legitimate points, right? I mean, they're just different heights, but they're not like undefined. I know. The problem is that it has no boundary points. Yeah? Do you agree with that? There's no boundary. We all agree with that. So then how can it be closed if it contains all the boundary points? I mean, I guess, does it contain empty? I mean, not that it's equal to empty, but does it contain empty? I guess. I didn't see none of that. I mean, you got a good point though, but again, this is our function here. We got nothing else going on, you know. There's nothing here crazy. So I would contend with it. I'm not going to say they're wrong. I'm gonna contend with it. That's just a definition thing, okay? And it might be one of these special cases where because it doesn't have any boundary points, you could say it is both. I don't know. To me, that just sounds a little weird. Okay, but I'm going to move on. I'm not going to get hung up on definitions because that's dumb. Cool. We got more time? Cool. Let's keep going. So we're trying to match this up to the picture, and this is what I really wanted to do from the very beginning because this is what's actually counting here. This is what is meaningful. Notice that we have a map, right? Contour lines. And it has these little hilltops. So we're looking for 4 little hilltops. Yeah. Yeah. Oh, yes. Yep, you're right. So if you look here, the Y, there's like 2 little bumps. Oh, man, don't use a green on that. No way. You can barely tell, but there's like these 2 bumps going on right there. And this x-axis is like there's a valley going through it. You can see that x-axis valley thing there. I know that it's not great, and I really don't like when it's not great, but there's no other options. That's why it's free. It's a pilot. but for future viewers, you might have paid. So. Yeah. So I mean, this is the reality of it. This is what we're looking for. Is this kind of stuff. Be a little careful. What do you think? I almost want to say it's due to like the same, not the last problem before that, where we saw that if X and Y are both the same, it goes out to a ball shape or a saddle shape. Correct on the concept. That's a parabola, and it's going to make it's wanting a cup. It's wanting the cup, right? But what about Y? Could be anything. Ooh, I love that. It could be anything. And so when you're graphing this, that's now a 2-dimensional, right? This was X. This is not any more Y. This is Z now, right? Because we're talking Z. So what's Y? Anything. Yeah, all the way across. It's like coming in and out of the page. Yes, the valley's on the y-axis. There it is, right there. You could see in this picture in particular, it's going up and down on the x-axis, right? That's my picture right there. This one, it's going up and down on the y. We don't want that. And then this one here was the like both. So if you had x times y, or something like that, or maybe like x squared plus y squared, then it would want to do that. Okay. Right. So which one of these contours would we choose for this? Remember your valley. It's going through the Y. B. Yep. Exactly. Because that valley, that straight line is going through that Y right there. Whoosh. Like that. I want to use different colors because it's getting a little eh. And so I got to also say that it takes a little bit of practice to kind of go back and forth. You can see that the answers are not hard. Okay. The answers are not hard, but I won't expect you to get it right every time. It takes time to kind of learn what the pictures look like. So for one, don't beat yourself up over it because it's how we learn, right? Um, and this is a perfect example of confusion. Okay. Hey, what does this picture look like? It's a plane. Okay, now what? And planes in particular are hard to detect. Okay, for me even, I don't even know how to make sure I have the right plane sometimes. I would ask you to guess, but I would also rather you tell me why you think that, or we can just play with it together. Yeah, positive, negative. The one thing that's confusing me on this is that it's both increasing and decreasing on Z, which would be yeah. So they're both doing that. That's one thing that's kind of confusing me on this one. I know, I know. So let's do it. Let's do it. Let's say that I have this set equal to 0 for a second. Let's start with that. That's an easy one, right? What's going on at z equals 0? What's going on the xy plane? Move this over. Yeah. Okay. So basically, I'm looking at this guy, right? And this is x, this is y, and this is literally the xy plane, the slice through it. So I'm looking for something that's going through the origin, and I don't know if that's going through the origin. I don't like that one at all. Yeah, it is. It's very confusing. See, planes in particular, man, I'm telling you, is a perfect example of but it's not hard. It's just kind of. Now, if I increase it some, let's go 10. Move it over. Yeah. And so at z equals 10, we've now shifted up some, and then we do it again. So it seems like our contour lines are kind of like this. Yeah. Okay. So we're ascending or descending down this way into quadrant 1 or into quadrant 3. So we're going up or down in quadrant 1 and quadrant 3. And so this one right here is going down in quadrant 1. Nope, that's not quadrant 1. Do you notice? That's not quadrant 1 right there. Where's quadrant 1? Look at the drawing. You see it? X and Y. This is quadrant 1. Is it going down? Okay. Is this going down? I know, right? Let's just see the answer. That's so great. Oh, it's that one. Oh, I was so focused that it wasn't that one. Okay, I see now why. I see it. Oh man, that's so dumb. But this is the last question. How about that? This is the last question. Let's figure out why. They drew their 3D coordinates like this. Is that what I normally draw? Not often. I normally do this. So let me recreate what they have over here. So I wanted lines that go like this. And so it's going to be going up or down this way, right? So here's my plane. You can see this line contour business. There's my plane. What theirs would look like then would look kind of like this. It's a flat piece right in front of us. And so, yeah, you're looking at a front piece. It's just like spitting right at you. But here, if you tilted it, you could see it going to the side. Even better, you can... That's not better at all, Chad. Even better, you can rotate it again. X, Y, Z. And so then what does that look like? Well, now it's coming down and spitting at you. So that didn't help at all. How about this way? X and Y and Z. And so again, we have those lines here. going up this way. So it takes a little bit of practice. Obviously, I'm not perfect either, right? I didn't see it. The pictures are not clear, okay? But you have unlimited attempts, and you got 3 answers, and you try it again, try it again, try it again, and that's what we have to do sometimes. Okay? Yeah. If we had for this the ability to take this and spin it around with our little mouse cursor stuff, that would be awesome. Just as a short demo, guess what? Desmos does it for you. So 3D graphing, and I think that we can do X, Y like this. If not, then we're gonna see. So what's that? 2x plus y.
Yes.
I mean, now look, so much better. And so this is your quadrant 1 is right here. I guess it was going up, not down. And notice it's going up, not down. I couldn't even get that from what they were talking about. Okay, oof. But if you looked at it from the top view, do you see that 2x, that y equals negative 2x line? When I go up some, do you see right here? This was 10 minus 2x, which I had graphed earlier as well. So use some Desmos. That'll help for sure. It'll help me too. Cool. Can I have that on the test? Well, we'll just not have this on the test. Thank you, guys. I'll see y'all later.